So we are more moving into, my research is more moving into the simulation related work. So I will talk briefly about my, previous research, but the research of today's topic is the simulation of electrochemical cell designs to improve the experimental accuracy. And I got my PhD in 2013 from University of South Florida. My PhD research was on hydrogen storage, basically on different material development areas. And after that, I worked on that's how I was actually started working on the lithium-ion batteries during the postdoc at Ohio State University. Okay, so that's my background. I also worked in some many years back in the industry as a mechanical design engineer mostly, and typically in the propulsion system design engineer. And my research is typically, I would call it more like an interdisciplinary research, and it is at the intersection of mechanical engineering, chemical chemistry, chemical engineering, and material science. And as Mehdi mentioned already, the energy storage is the biggest part of this, and this is the very hot topic, as you all know, moving forward. The carbon capture and storage is going to be also definitely be another hot area, and buildings, minimizing building energy use, striving for zero emission buildings, etc., are also is my interest. Moving forward, folks, let me talk about, again, this research is actually, I recommend you, all of you, to explore these opportunities. I don't know if UDC is eligible for that, but Department of Energy, since Mehdi already mentioned, this is a NASA center, and you are working on some energy-related projects. So the Department of Energy has something called Visiting Faculty Program. Now, of course, if you are listening to this seminar and you are a graduate student or even a postdoc, doesn't matter really, you can ask your advisor to apply for this program. And if you are eligible, again, if the university is eligible, so you can go there and with your faculty in the summer do research. So that's what I did in the summer at National Renewable Energy Lab. They have lots of research going on there about the energy storage area as well as solar energy technologies. So this is part of that program. Of course, originally this was supposed to be the in person, like I was going to go there, but that's why the research actually proposed was experimental, but due to COVID, we moved to simulation related work. So that's what I will be talking about, the how we can improve the experimental accuracy based on the electrochemical cell designs and how we can simulate them. Okay, so again, I'm assuming not all of you guys are familiar with these, this kind of research. You may be working on lithium battery research, but not many people are working on in situ techniques or development of these techniques. So I'm going to talk about that a little bit. And then I will introduce you some different designs, especially this is for atomic force microscopy and scanning electrochemical microscopy. So SECM stands for scanning electrochemical microscopy. All right. And then we will talk about why the simulations are important. And all these simulations, of course, you can develop your own code, but in the limited time available to me, I use a COMSOL. Some of you, I'm sure, are familiar with this. The software package, this is multi-physics simulation software. So it lets you to combine multiple, physics into the single, problem. So it is quite efficient in doing that. So I use that one, and I will show you some preliminary results. This is an ongoing work; it's not finished yet. So this is a very like recent work, few months old, I will say. And I will just mention some, future work on this work and some conclusions. So, folks, typically, as you know, lithium-ion batteries are moving forward will be very, dominant in the energy storage area, both stationary and mobile applications like cars. So when we characterize these batteries, typically we have mainly two options. One is like the X2 techniques, and the other one is in stew. Sometimes you may see in operando. There are slight differences between these terms in operando and in stew, but I will just put everything under in stew techniques for now. So the X2 techniques basically are the once take the battery out of the let's say you install it into a car or some other application, take it out and dismantle it and analyze its surface, or you discharge it, etc. So you can test its material properties, for example, if that's your goal. That the insta is usually when you are running the battery and you are trying to get useful information. Why this is important? Because insta techniques are required because most of the time the battery chemistry is quite complex. So in the nanoscale, atomic scale, there are multiple phenomena going on at the same time. So insta technique is very useful because you can only observe it in certain time during the battery operation, for example, certain state of the charge, etc. So that's why in-situ techniques became highly popular, and it is even getting more and more popular. And also another thing moving forward with the battery characterization is multimodal experimental techniques. So what this means is typically now today it's not enough just to go, for example, use atomic force microscope and just observe the for example, morphological changes. That can answer some questions, but again, due to the complexity of the nanoscale phenomena going on, typically you need to use multimodal experiments. By this I mean, for example, if you are running AFM, you may be adding for example, the Raman spectroscopy to, for example, get both chemistry specific data, on top of that some morphological data. So that's why moving forward, instant multimodal techniques will be important. Okay. And I gave you here the two, for example, very important areas that these kind of techniques can be highly useful. One of them is, as you know, the solid electrolyte interface. That's the layer that forms on typically on anodes when the battery is in operation in the beginning, especially, but it's an ongoing process. So that's something you can observe. And new, more hot topic in the battery area is these, metal anodes or silicon anodes. So those are typically, to improve the energy density. The field is moving that way. And if we are talking about metal anodes, for example, lithium metal anodes, without any graphite or any other host material, so then you have an issue with the dendrite formation, those pikes that forms in the lithium that can make a short circuit and kill the battery or cause a thermal runaway. So the dendrite formation anodes is, for example, another very useful another area where you can use this multimodal and in-situ techniques um, for observation of this phenomena. Another benefit of in-situ techniques, folks, is when you disassemble the battery, now there will always a high chance of introducing some artifacts, because when you remove the battery, disassemble it, this may cause some artifacts. Like, of course, you do this in a glove box, typically in a inert atmosphere, but still, whenever you are removing it, for example, you may scratch the surface. The SEI layer, for example, the one I mentioned, so the electrolyte interface, is very thin, so you can easily damage the cell. And when you are transferring to other experimental tools, you may be introducing some oxide layers, etc. So it is really way more favorable, beneficial to do if you can institute techniques. Of course, there are limitations. We will talk about that. So the last bullet point here is mentioning again the multimodal technique. So most of the phenomena is complex, so single experiment technique highly enough to observe this. Okay. So let's look at some of the experimental cell designs. Now again, this presentation is about how to improve the institute AFM or scanning electrochemical microscopy techniques. But I'm going to give you a little bit a broader overview of like how the in situ cells usually look like, how they are different. Now, again, for most in situ cells, you need some kind of a window or an opening, folks. For example, if each design is different, of course, I mean, depending on the experimental techniques. For example, if we are talking about optical microscopy, light spectroscopy, or X-ray diffraction, what we need is we need a window, okay? Some kind of a transparent window so we can, we can interact with the battery surface remotely without changing anything inside the battery. Okay, so typically they have some kind of a window. As you can see, this is an example of an in situ Raman cell. So that's how we interact with them. Another one is, for example, another important technique is the scanning electron microscopy or transmission electron microscopy in situ cells. This time, of course, the way we observe the cell is using electron beams. Now, this creates some another challenge. That is the electron microscopy typically requires a vacuum environment. And as you know, most of the batteries, commercial ones today, is relying on liquid electrolytes, okay? But that is typically not possible to use it in the in-situ TEM, for example, transmission electron microscopy. So typically they would use solid electrolytes, okay? And due to the nature of the TM as well, it's very small. You need to make these cells are either fabricated by nano fabrication techniques, so it is more tedious, typically TM. Last one I want to mention is this scanning probe techniques. So this is an umbrella term that includes all sorts of scanning probe techniques, like for example atomic force microscopy, scanning transmission electron microscopy, scanning electrochemical microscopy, Kelvin probe microscopy. Like there are lots of names. So the goal or the idea behind this scanning probe techniques is, so you have some kind of a probe. Let's say you want to measure just the surface roughness. That's your goal. That probe approaches to the surface. It gets very close, like nanometer levels close. Okay, so once it gets closer and closer, the surface and the probe will interact, and the surface and the probe will push each other. So basically, if you follow this surface with a piezo device, okay, in x, y, and y direction, you scan the surface, so you can be able to get the surface roughness or surface features or morphology data from the material. Okay, so this is the logic behind the atomic force microscopy. Okay, so typically you shine a laser on top of the probe, and that's how you can understand how much the probe is moving, because probe usually moves very small, so you need something like very accurate, and that's the laser. Okay, now only thing you need to folks note here is, again, if you are not familiar with the AFM or probe techniques requires an opening, like in uh, you know compared to these optical techniques like you see here, the Raman or other cells, these only requires a window, like the cell itself is still sealed. And why it is important? Because liquid electrolytes have a very low boiling point, so it will quickly evaporate. So in this case, for example, for the optical light spectroscope technique, that's not an issue. But for the AFM and probe techniques, typically, you need some physical opening on the cell so your probe can approach the surface. So that creates some other challenges. One of them is, again, the electrolyte evaporation. Okay, so that limits the amount of time you can spend collecting data. Okay, because of the electrolyte evaporation, what happens is now the current distribution inside the cell is a strong function of the concentration of the lithium salts inside the electrolyte. Now, if you are evaporating the electrolyte, then that concentration will be, for example, instead of 1 molar, that's typical in most of the lithium-ion batteries, over time, because of this electrolyte evaporation problem, that will become more and more, higher concentration. Maybe it will become 2 molar, etc. So this is gonna change the characteristics of the battery. So, I mean, with any experimental technique, as you appreciate, our goal is to get the real working system as close as possible. So, but those kind of interferences will affect your results. So you need to take that into account, or I mean, you can do post processing and to fix that issue, but better if you can address it in the cell level, prevent that electrode evaporation, or just minimize it at least. All right. So this in this project, what we did was, we analyzed some of the in-situ cell designs for atomic force microscopy. The scanning electrochemical microscopy part hasn't been done yet. But the main difference between the SECM and the this is the ECAFM is stands for electrochemical atomic force microscopy. Sometimes people only use AFM, so they are like interchangeable terms. But the main difference is this, folks. So for AFM, the probe dimension is usually in nanometer levels, like 10 nanometer, for example, the tip of the probe. Okay, because you need typically that's why you typically use AFM to get high resolution, surface feature data. For scanning electron microscopy, the goal is not really to get the features. It is more to collect some, chemical transportation information, etc., species transportation. So probe is much larger there. So I'm not going to go there now today, but I just know the difference. One is very small, the probe. In the other one, the probe is very large. I mean, large means like 20 micrometers. It's not like millimeter level still, but it is a microelectrode. It is in the AFM, it is a nanoelectrode. You can think like that. And this is, again, I'm sure all of you are familiar already. This is a typical, cross-section of a rectangular prism battery. So you have this, typically in batteries, you can think like this. There's a cathode, there's a separator that is, in between the anode and the cathode that prevents electrical direct contacts. And our electrolyte is typically, inside the battery, and it's usually soaked or stored in the separator pores. So it allows you to have a lithium ion diffusion back and forth between cathode and anode. So lithium ions will diffuse from the, electrolyte through separator, and electrons will flow from the outside of the circuit. So that will, that will complete the circuit. Okay. So, and important thing here is, folks, is if you look at this cross section or any other type of battery like coin cells, pouch cells, etc., anode and cathode surfaces are like directly aligned. Like let's say the surface areas are like very minimal differences there you can observe, but typically anode and cathode are facing each other. Okay, and they are typically under slight pressure. So this allows us to have nice contact. Okay, there's no gaps, air gaps, etc., and the diffusion length will be also minimal. So we don't want lithium ions to diffuse, like a very long distances. The smaller, the better, right? So surface areas are aligned. So that is very important, similar and directly facing each other. Why? This will affect your current distribution. And that's what actually we will be observing with the different experiments, which I will show you in a bit. And these are some cells designs. I will go quickly over these. I worked on during my postdoc time at Ohio State. So in the literature, folks, if you go over these very early works, most easy or convenient way to do this apply institute technique is to use a coin cell. All you need is a coin cell. What you see here is a coin cell, but top of that is like punched top of the casing. So only you see the black portion is the cathode. This is the actual photo I used in an experiment. So this is the black cathode, lithium iron phosphate in this case. And next to that, you see slight white area. That is the separator. Okay. And then comes your coin cell. Okay. Now, this is very easy to assemble. You need a crimping machine. There is something called crimping machine. You need a specialized tool. but it is not a hard job to assemble this. The issue with this kind of a coin cell is, as you can see, I mean, I'm sure you have seen some button cells or coin cells in your life. So they are very, shallow. Like their height is like maybe, 5 millimeters. And typically you don't have much reservoir volume to have electrolytes. So most of my experience with using these cells is electrolyte there would evaporate very quickly. So the cell wouldn't work, after a while. So that is one of the, because, for this battery to work, so all this black area should be slightly, covered with the electrolyte all the time, but it will typically evaporate very quickly, okay? Because it's very shallow. There is very limited area. So one improvement over that is we had this, I call this lithium wire cell. Now this has a very large, reservoir volume, and this, in the middle, the where I'm pointing with the laser, that brownish area is your copper current collector. So on top of that, the cathode goes, and the around that you put a lithium wire. Okay, so that's your counter electrode, and you fill all this gap, white area, that all that area with the electrolyte. So this is a little bit better, like you have way more electrolyte. Even if it will be evaporating still, I mean, it's inevitable. So, but at least, you will have a large volume, so at least, that changes will be minimal in the electrolyte concentration. The problem with this one was the repetibility. So the putting that lithium wire around this, the cathode is a very tedious process, and it may, move around, etc. Like it is had some kind of other practical, difficulties. So the one I developed at the end was this lithium foil cell. This is specifically designed to be assembling glove box, and it only needs a, screwdriver. You have these, plastic screws. This is um, this is built using I don't remember the material, something like a very, electrochemical resistant material. So plastic, and it is easy to assemble inside a glove box. And the counter electrolyte electrode fault in this case is a lithium again, but as you can see, it is like a ring structure. So you can basically use a puncher and prepare your lithium counter electrolyte in advance, always the same size, because you know exactly how much, the dimensions in inner diameter is, outer diameter. So it is very easy to prepare this counter electrode, and it is repetitive, like you can reproduce the results. So this is the cell we have used, and the simulations here will be also showing something similar to this as used. So this is kind of, one of the typical, not coin cells, like in situ AFM cells. This is for atomic force microscopy, but you can definitely use this for other, probe techniques easily. I mean, there's no difference there really, and assembly is easy. Only thing you need to, again, since you are seeing here the exploded view, folks, you can here observe, like, for example, this is the working electrode. This is, covering all the bottom area, but the lithium counter electrode is like a ring, right? So that will create some non-uniformity in the current distribution. As we mentioned earlier, like normally what you would have is you would have, let's say, 1 centimeter square of, square, assume 1 centimeter by 1 centimeter, cathode. The most ideal condition is to have the same area counter electrode facing directly to, the working electrode. So your, diffusion length will be the minimal, and, also the current distribution is gonna be, uniform. Why it is very important, current distribution? Because let's say if your current distribution is concentrated on the areas, certain areas, what will happen? So most of the current lithium ions will flow from there. So they will accumulate there, and those parts will age faster. Like some areas will be highly utilized, some areas will not be highly utilized, or maybe it is not even utilized at all when you charge and discharge. So that creates a problem. That will create a, your battery to prematurely age certain areas. Although maybe 80% of the battery is perfectly fine, but if your certain areas aged a lot, then it will create some issues. For example, it can create some short circuits from there because of heavy utilization, etc. So it is not ideal. We want uniform current distribution as much as we can. Okay, of course, in a typical commercial battery, this is not an issue. But when you do the experiments, how you can attain the same uniform current distribution, that's important. Okay, so also, this will allow us, folks, to observe the intrinsic surface phenomena happening when we have a current distribution. Some of the things that can happen again with the non-uniform distribution is, let's say you are working with the metal anodes, then you can observe excessive dendrite growth. Okay. Also, deletion of the cathode anode particles will be non-uniform. Some parts of the cathode or anode will be lithiated. Some parts will be not lithiated at all. Okay, so those are all issues. Again, from the experimental technique, folks, I don't know how many of you are doing these experiments, but when you, for example, measure in the lab the voltage of a battery, all you get is the average value. Like you only get the average value from, let's say, all the current collectors. That's where it is connected. But in the cathode level, that may not be the case. Like, let's say you are observing 3.5 volts in the cathode at some point, okay? But maybe, some parts of there are overcharged. Overcharging is an issue, as you know, especially for certain cathodes. For lithium iron phosphate, that's a less issue, but there are some lithium cobalt oxide, for example, is like less stable. So that's a big issue. So what you are reading there is basically the average value, but you don't want really what's going on, within the, actual surface. So that's very important. So these will, of course, will create some artificial, artifacts in your, battery measurements. But also note that, the whenever we assemble batteries, there will always be some kind of a surface inhomogeneities. But we don't want to, introduce more than that. Like we want to keep it as, as it is, because surface inhomogeneities are part of the lithium-ion batteries, and that's inevitable because of the manufacturing process, the differences in the materials, etc. So it is not going to be eliminated completely ever. But again, when we are doing our experiments, we can try to minimize that, additional artifacts that is introduced. All right. So this is, like as I mentioned, folks, experimentally, you cannot really measure the, local current density. All you can measure is, the, average from the whole surface. So why simulations are, very useful, because this way we can measure the, these current distribution locally. That simulations will allow us to, do that. Okay. Also, another benefit, of course, is if I can, or you can, anyone can quickly scan through a lot of different designs, like, for example, form factors, diameters, the height of the cell. We can do that very quickly using electrochemical simulations, okay? There is something called, for example, parametric sweep. So this is I'm sure that they have in other software too, but the one I'm a little bit more familiar is COMSOL. In COMSOL, you have this option. You can, set it like, for example, I want to scan this diameter from 5 to 10 millimeters in 1 millimeter increments. So it does for you automatically. You don't need to really do anything else. So it's very quick. Multiphysics phenomena is very important. Now, so far, I have been talking only about the electrochemical current distribution in the cathode surfaces. Now, why multiphysics is important? As I mentioned in the beginning, electrolyte evaporation is a big issue. Okay. Now, for example, I can, it hasn't been done yet, but that's again the future work. For example, you should be able to integrate the electrolyte evaporation and its effects on the current distribution. Okay. This can be also simulated. So this is kind of a multiphysics phenomenon. On top of that, let's say there are some thermal gradients. Now we know thermal gradients affects the current distribution. Typically, you don't want any thermal gradient at all in when you are like when you start your experiment, everything should be in thermal equilibrium. But even very small temperature differences, okay, that may affect your results. So, for example, you can study the effects of these thermal, gradients. So that is, you can couple multiphysics phenomena can be coupled. Coupled multiphysics can be studied using these techniques as well. Okay. Um, so those are the some, things you can study. One other thing I haven't mentioned, folks, is to prevent this electrolyte evaporation. This was both experimental and a simulation project that's ongoing. So, for example, once you have the electrolyte evaporation, another fix for this problem is you can add with a micro pump, because the electrolyte volumes are very, very small. You need something like adding like microliters over an hour or something. So micro pumps can add like electrolyte over time to like, yeah, since you know the electrolyte evaporation rate, you can add the same amount of electrolytes during your experiment. So this will keep things in check. But of course, when you add this, liquids, they may, create some, fluid flow conditions inside the cell, which is also is not, desirable. Okay. So because, the conditions for batteries are static. I mean, there are like flow batteries and all that, but in a typical lithium-ion battery, strictly talking, we have static fluid, like only, ion diffuse back and forth. Okay, so there's no fluid flow there typically. So this can be studied as well. Like it is like gradually like making more complicated models is up to you. So that's another benefit. So I'm going to show you here the interface from the console. So they have this electrochemistry module. They have some more modules. I'm not familiar with everything actually, but I'm just gonna show you this electrochemistry part. So here you see three main things. Like first is the primary current distribution. Okay, so typically this is the recommendation. By the way, folks, also note that until this summer I didn't really do any electrochemical simulation. I mean, this is something also very new to me. So COMSOL recommends the when you start your model. I mean, this is, I think, applies to any model. So you start from the very basic models. Okay, so primary current distribution neglects the activation losses for the charge transfer reactions. Now, again, we don't have time to cover all these theoretical backgrounds here, but typically when the lithium ion flows, okay, it flows from cathode to anode or the other way. So this is when the charge transfers from the ion to the cathode or anode. So there are some losses there. Like there are like in each part of the process there are some resistance in the process. So this very basic model neglects those activation losses. So it is assuming it's seamless, like it happens right away. Okay, so that's what we call charge transfer in here. Okay, and the secondary current distribution interface accounts for those losses. Of course, these activation losses, you need to enter some parameters that are taken from some other experimental works already in the literature. And the most advanced model in here is the tertiary current distribution. This relies on the Nernst-Planck interface. That's the equation, also Nernst-Planck equation. So that is accounts for transport of species through diffusion, migration, and the convection. So those are the possible ways any species can transport from one cathode to another one, electrode to another one, right? So this is accounts for that. So this way we can express the variations in the composition. So this tertiary model is still, I haven't done that yet. I did with the secondary one. So, but I'm just introducing you what you have in COMSOL here. Okay. So This is the work plan. So we studied the current distribution first for the some electrochemical chemistry AFM electrochemical AFM cells, and we did some parametric sweeps to see how these geometric changes affect the current distribution. Okay, so the let me see how much time I have. Okay, I think I am a little bit uh,
It's
behind.
okay, doctor. If
Okay.
if if you would like to continue, we will take advantage of that.
Okay, I think I have like 6, 7 slides, but yeah. So,
Would be great.
all right. So this is the first part. I mean, the one that's done is this, geometric, analysis of different, cells is done. We also did some comparative work, like because when you do the simulation the first time, you want to compare with the literature work. So that's what we did as well. The third, and fourth action items are pending, folks. So again, like thermal gradients, as I mentioned to you, are important in current distribution, and also electrolyte evaporation needs to be still studied using the simulations. Now, let me now show you some results and my model. So again, to keep things simple, because the I run these simulations using a regular desktop. This is not like a supercomputer or anything. So I wanted to have this as simple as possible. So the AFM, Institute AFM cell I have shown you can be modeled by axis symmetric model. Okay, so this is my symmetry axis. So what you see is to the right, this is the working electrode, this purple, okay? So width is defined in the simulations, and the height, because height determines the electrolyte reservoir. All this, bluish area is the electrolyte, and then on top, counter electrode is here. Now, as you can see, this opening, I mean, this is the opening because AFM head is going through here and approaching the working electrode surface, okay? So this head, will go through there, so I need this opening, but how much I can close this, of course, will depend on the specific experimental, tool, but I also studied, how this, expanding, making is, wider and wider, this counter electrode, how it would change the, results, the current distribution. So we studied that one too, okay? Otherwise, I mean, normally, again, in a regular battery, working electrode and the counter electrode has the same surface area, okay? So the electrolyte chosen here is ECDEC11. This is by volume ratio. This is very common in most of the lithium-ion batteries, and we set both of them were assumed as the lithium. Okay, counter electrode in the simulation set to the 0 volts, and the working electrode is set to the -1 volt. Okay, and this is the configuration. So working electrode is fixed, so it's not gonna change. There's no need to change that one for now. I mean, you can simulate a specific system, but for in general study to understand these parameters effect, you don't need to change that. So that's constant. Counter electrode has been changed from like 2, 4, 6, 3 options are tried, and the height has been varied from 2 to 8 millimeters. Okay, so shallower cell, taller cell with larger volume. Okay, so what you see here is the current distribution, folks. Again, this is my symmetry axis, okay, and this is the current distribution. Now the numbers here is the absolute value of the numbers on the y-axis is not really very important. Just pay attention to how the current distribution changes from the symmetry axis. This is, by the way, now what you are seeing is the current distribution over this working electrode surface. When I said, there is no way you can measure this by experimental technique, that's what I mean, because when you have a experimental setup, on top of this working electrode, on below of this working electrode, you have a counter electrode, right? So counter electrode is where it is connected to the circuit. So you measure average of all these. Like let's say instead of seeing a current distribution like this, you will see something like like a average value, like something like this. You can never capture this distribution. So that's the that is something you can only do with the working electrode. I mean, sorry, simulation simulation work. Okay, so what I'm showing you here, I'm not showing you everything, but I am showing you the height is now kept at 4 millimeter. So height is same, okay, for all the simulations what you see here, but the counter electrode is increased from 2 millimeters to 6 millimeters, like 3 options you can see here. Okay, it is we never studied the same working electrode is, as you remember, it is 8 millimeters. We never studied that because you always need to have some kind of opening, right? So there's no point in simulating the, that will be the baseline. But I mean, if it was done, you would see a, like horizontal line. Okay, so that's what you will see. There's no, this, change in the, current distribution. So as we expected, folks, right? As common sense, as the counter electrode gets larger and larger, our current distribution, for example, the red one is the one with the largest counter electrode. So your current distribution has very minimal, variation. The maximum variation is in the blue one. That's the smallest counter electrode. Okay, so that's the goal or the results from this simulations. So again, we observed the same trend for all other heights, but I'm not gonna, I didn't include those here. Another thing we studied is the effect of height. Now, how the height affects the current distribution. As you have larger and larger reservoir, lithium ions will be diffusing from top to the below or the other way, right? So in this case, it's going from top counter electrode to the working electrode. So if you have a larger and larger, height, okay, taller, cell, lithium ions will have more time to align and uniformly distribute, okay? So of course, these are all on steady state, but still, like as you give them like a higher area, like to maneuver, okay, the current distribution will be better. Now, what you see here is the counter electrode is fixed at 4 millimeter, but the height is changed from the shallowest cell is 2 millimeter, and the highest one is the 8 millimeter. Okay, these are all practical and reasonable numbers, folks. So as we increase the cell height, as you can see, this like this is the highest cell, the largest cell I have. It's almost uniform, the current distribution. But as you make it shallow and shallow, you see a significant change again. Okay, so that is again another results we get from this design, I mean simulation. So we want the cells as deep as possible we can think of. Okay. And again, this trend holds for different counter electrode size. But of course, there will be some limit, folks. You cannot make it like 1 meter deep, of course. I mean, there are some limits. But again, usually it is more than few millimeters. So you should be able to apply these, guidelines. So this is one study we wanted to, repeat by ourselves. This is an optical microscopy study observing from the literature. This is not my work. What you see is they optimize the cell. This is the current distribution of the optimized cell, and this is the current distribution on the working electrode. So optimized cell has very, a flat current distribution as opposed to this dashed line where you see non-optimized cell. This is the non-optimized cell, folks. That's more shallow. Again, this also aligns with our previous findings. As you remember, deeper the better, right? So this is the optimized cell. So what we did was we simulated this. We created this same model just to make sure we are getting the same results. So this is their results. Now they did like a full scale 3D model. I didn't do that. Again, there's no need for that. So we did a 2D axisymmetric one, and this is showing you the electrolyte potential distribution within the cell, and it is the same. That's how we found. And the current distribution also in their work, it looks like this. In our results, again, this is axisymmetric, and this is similar. The numbers doesn't exactly match because again, first thing is they use a tertiary model. I'm using a secondary model, for simulations. So that's one of the reasons. Also, the parameters, folks. Not all the parameters, unfortunately. This is something always disappoints me when I read some papers. I cannot find all the data to repeat the results. So they include some stuff, exclude some stuff. So that could be another reason for this discrepancy of the numbers, in the current distribution. But overall, there's a good match. So because again, like I'm studying this new work, so I wanted to make sure everything is going as planned. So more work will be done, folks. For example, this is again from the literature. What you see here is, as I mentioned, like AFM versus microelectrodes. This is the current distribution in a cell like this rectangular cell. This is the physical, photo of that. As the probe goes through the surface, you'll see there's some depression in the middle of this, or just underneath the probe. What that means is the current distribution or the flow rate will be always less compared to the other parts in the in these experiments, scanning probe techniques. This has a lot of practical outcomes, results from here. One of them is because in the scanning probe techniques, you are just scanning underneath the probe. You don't probe, for example, somewhere like -6 or 6. You are exactly scanning somewhere near 0 millimeters. So you should also keep in mind that current flow rate is less than what you set it up at the beginning. So you can correct your experimental results based on these simulations as well. So that's something I am planning to work on. All right. And this is the kind of the future work, folks. Again, some of them are already done, the first and second item. I will be also working more on the thermal gradients, the fluid flow, electrolyte evaporation, and to prevent that fluid flow, using a pump. These will be studied as well in future. Okay. And again, as a result, typically you want to have as large contour electrode as possible, and also you want to have as deep shell cell as possible when you design any electrochemical cell for these experiments. Okay. And thank you for your time, and I am happy to answer if you have any questions.
Thank you so much, Dr. Demirocak. It was very interesting and informative, and we definitely take advantage of that. And it provides us with a deeper insight into the field of research. So if any of the students have any questions, please make it.
Sure, sure, my pleasure, folks. I wish you all the best in your studies. Yeah, yeah. I mean, you can.
Okay, no.
Yes.
Yes, sure. So, no questions. I'd like to introduce to Dr. Zhu. So, my current supervisor and director of NASA Chemistry at UDC. However, he had to leave the meeting 15 minutes ago because we have inspection by NASA guys from our labs, and that's why he had to leave. Unfortunately, we didn't have this opportunity today.
Yeah, I saw the messages in the chat, but I couldn't read when I was talking. Yeah.
Yeah. We will be we will be in contact, doctor. We will be in contact with you and Dr. Zhu, so for further collaboration.
Sure, Mehdi.
Okay. Yeah,
Thank
thank you
you.
so much. Thank you so much.
I
It was
would I
great.
would request all the participants to please take the survey before you leave. The link is provided in the chat box. So if you click the link, it will directly take you to the survey page. So I request all the participants to please take the survey before you leave. It will help us to organize a better seminar the next time. So this was an excellent experience, Dr. Damira, to have you today here.
Thank you very much for arranging everything. Thank you.
Thank you.
Yeah.
Have a nice day.
Thank you. Thank you. Bye bye, doctor. Take care.
Take care. Have a nice day.
Bye bye. Bye bye.
Thank you. Bye bye.
Bye bye.
Excuse me,
Yeah.
have you posted the
Yes,
chat?
the link. Okay. Just a minute. Sorry. Okay, it is there now. Yeah,
Yes.
sorry for that. Yeah. And please let me know if you guys have any questions. Okay? Yes, please.
No, I'm fine, thank you.
Okay, okay. Are you guys good with the survey? Humble? Checkley?
I'm still working on it.
Ah, okay, okay. Please let me know if you have any questions.
Thank you very much. I enjoyed it a lot. I think it was very interesting and very eye-opening in the battery technology. And I thought it was very similar to what's happening in VLSI design, other parts of electronic design. So I just finished the survey. I think I'll be leaving and I hope to see you on another seminar.
Sure, thank you very much. And I'm glad that you liked the seminar and it was informative.
Okay, bye-bye.
Bye bye. Thank
Yeah, I'm
you.
also finished, so I'll be leaving to see you in the next seminar.
Great, thank you. Thank you. Hey, Takili.
Hey,
Hi.
good, good. What's up? What's up?
But you cool?
Cool. Yeah, cool. I almost done. I was taking kids. Just give me a second, okay?
Yeah, take your time, no problem. Take your time.
All right. I just submitted. Thank you
Okay.
very much for your time and very good time. He used very precise time and also well organized. We need that kind of person.
All right. Yeah. I'm glad that everybody enjoyed the seminar and it was very good as
Yeah,
well, like the information perspective. So I hope
exactly.
everybody can take advantage of this kind of seminar and grow in their research areas.
Yep. Yeah.
Great, great. Okay. Are you
Very
went
good.
to university today?
Oh no, my wife is working today.